Our next speaker is Jack Koolen, who is with us, and we're really happy that you have time to give a talk on this workshop. So the floor is yours.
Okay, thank you. So I will talk about sesqui regular graph with fixed small eigenvalue, and this is based on joint work with Baron Michael, who's sitting next to me, but you don't see him. Yichang, who's now as a lecturer in Shanghai University. Yang, who is now working in Samsung company. Ge is a current PhD student, and Masoud Rehman is working in Turkey. So I will define strong regular graph, co-edge regular graphs, and sesqui regular graphs. And then I will talk about some ideas about the proof, and then I will give examples of sesqui regular graphs, because are they close to strong regular graph or are they not close to strong regular graphs? I think they are not close to strong regular graph. So, but sometimes they are very close. So this is just to make sure that we are talking about the same thing. So we have a vertex graph with vertex set Vg, edge set Eg, which is a subset of the two subsets of Vg. Then we have the adjacency matrix, and most of this talk is about the smallest eigenvalue. But sometimes I talk about the last eigenvalue. Okay, so we have also notation that H is subset of G. Then we mean by that is that H is an induced subgraph of G, and and the other one is not an induced subgraph. Yes. So, and if every vertex has k neighbors, if an edge of a vertex is incident with exactly k edges, then it's k regular for it. Yes. So strong regular graph is it has 3 vertices. It is k regular. Every pair of adjacent vertices has exactly a common neighbors, and every pair of distinct non-adjacent vertices has exactly c common neighbors. And here's the easy example, the pentagon, that's 5, 2, 0, 1. And you have, of course, the Peking graph, which is in 10, 3, 0, 1. And we will see that not always A has to be 0 and not always C has to be 1. We will see examples of this later. So Neumayer showed several things. So what he showed is either if you have strong regular graph with parameters V, K, A, C, and you fix your small cipher minus lambda, then it is either a complete multipartite graph, or C is bound by a function in lambda of the order 4. And we have only 2 cases where equality holds, namely for C is for lambda is -2, then you get 8. And there is the Clefley graph that has equality, and for lambda is -3, we have the complement of the McLaughlin graph that has C is 81. That is what we know on this moment. And the 4 theorem is usually contributed to Neumayer, but it is really a theorem by Sims, although he never wrote down the proof. In a survey paper in the 1970s, I believe, they attributed this theorem to Sims. So what he showed is that C is either a complete multiplier. If you fix your small cipher minus lambda, then either it is a complete multipartite graph, a Steiner graph, a Latin square graph, or C is a finite set of strong irregular graphs. So So the number of vertices is bounded by some constant. And the last time Michael talked about -3, how big this set is for lambda is -3. So what is co-edge regular? Yes, we have regular, again, K regular. But now for every pair of distinct non-adjacent vertices, that's exactly C common neighbor. So you remove the A part of the strong irregular graph. So they are quite closely related to strong irregular graphs, co-edge regular graphs. But there are many more examples than only strong irregular graphs. For example, you can take the clique extensions of strong irregular graphs that gives you those, and also say the T times S grid is a co-edge regular graph with Cs2 where A is not a constant because if S is not equal to, if S is equal to T, then you have get a strong irregular graph, and as S is not equal to T, then you don't get a strong irregular graph. So we show the following theorem with Yang. So we fix lambda, and then there exists a constant C1 of lambda, such that if she is connected co-edge regular graph with parameters VKC and lambda, the small value of C is at least minus lambda, then either phi minus k is close, phi is very close to k, or C is bounded by constant C1 and lambda. So either it is close, so you get either C is bounded, or if it's not bounded, then it's close to K. That's what this says. And you can to show that item 1 that you need to use the Allen-Papanes theorem, and because of the inequality in 1 is sharp, as there exists for every K an infinite family of bipartite Ramanujan graphs with valency K, as shown by Marcus and others. To obtain that this is really sharp is that you take the complement of those graphs. So that is where you get this equality. There's this paper in Annals of Mathematics that they showed it. And okay, so now the other way to show item 2, we need Ramsey theory. The main reason we can use Ramsey theory, that does not exist an induced lambda squared plus 1 law, because that will have small xi value less than minus lambda, and by the interlace theorem we get a contradiction. We have no explicit bound for C1 lambda, but my guess is that this bound for strong irregular graph is the right bound, but I don't have a proof. So now we go a little bit further. We had co-edge regular. Now we go co-edge regular. So now we define sesqui regular with VKC. What is the difference between co-edge regular and sesqui regular? If you take any two non-adjacent vertices distinct, then either they have 0 common neighbors or they have C common neighbors. That's only two possibilities. So connect sesqui regular graph with diameter 2 is same as a co-edge regular graph. So then, because then you don't have distance 3 in your graph, yes? And you can do the same theorem as with what we did with Yichang for the class of sesqui regular graphs. You get the same And the proof is exactly the same. But the motivation was we were looking at co-Israeli graph because the motivation came from distance rally graphs. But we learned later on, we understood that we only need the sesqui regular condition. So that's much weaker. And I will show this, that it's really weaker than co-X regular later. And so now what is the difference now? Before we had C, that C is bounded by C1 of lambda or C2 of lambda. Now we let K be very large. Yes, we fix small eigenvalue and let K be very large. Until we have either K is close to V or C is a mode lambda squared out lambda minus 1. So, but we think that item 2 is not tight, but so now we have a good bound for C, but the valency has to be very, 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 very large. Because we use Ramsey theory, so to use that, we need to use that the K has to be very large. We want to find large cliques. For stronger hierarchy, we know the bound is lambda squared. And so we wonder whether C has to be at most lambda squared, or I think that's probably true. But our proof needs to be, will not exactly work for lambda squared times lambda minus 1. We cannot improve to lambda squared because we don't have on this moment enough information. So that is, this is the paper is submitted to linear algebra and applications. So now we look at -3. For -3, we can do a little bit better than for general small eigenvalue. So the result before says that either K is close to V or C is at most 80. And we can improve this to the following theorem. So we can show that either C is K or C is K minus 1. And we know that exactly what are the graphs. Then instead of C as most 80, we can show that C is either 9, and we know exactly what is the graph. We know how to construct all the graphs. They are always strong irregular. Why this is exactly true, we don't really understand. It falls from the proof, but after we classified them, we knew that they are the Steiner graphs, but we did not know that it has to be the Steiner graph when that the graph has to be strong irregular when we started to classify. And then the fourth item is C is a most 8. So either C is 9 or C is a most 8. But for C is 9, we know exactly the graphs. So now we look at the two graphs. I should maybe do everything here. So we take the T-claw. That is one vertex associated to T vertices, and the T vertices have no edges between them. Yes. That has small sign minus squared of T, so the lambda min of K1T goes to minus infinity if T goes to infinity. Now we look at the graphs K tilde 2M. So what you start with the complete graph K2M, and then you add an extra vertex, then you join to exactly M of the vertices of the clique K2M. That is. And it looks very close to a clique, this graph, but the amazing thing is the smallest eigenvalue goes to -infinity if m goes to infinity. It's not difficult to see. This was observed by Hofmann. And I will come back to this later. So now I will look at some results of Hofmann. So we look at the graphs with small eigenvalue at least minus lambda. And by interlacing, if lambda min h is less than minus lambda, then h cannot be an induced subgraph of T. This is by the interlacing theorem. And so this gives the first item of following theorem by Alan Hofmann in 1973. Let C be a graph with small lambda min. Then there exists a positive integer T, and that only depends on lambda min, not on the graph T, such that neither the K tilde 2T nor K1T are induced subgraphs. That falls by the induced because they go, if T goes to infinity, the smallest eigenvalue go to -infinity. So that is why. But the second item is very interesting because that is somehow strange. So suppose that you have a positive integer T such that neither K2 tilde T is an induced subgraph, nor it does not contain K1T. Then there exists a positive integer lambda of T that the small eigenvalue is minus lambda T. And this lambda T does not depend on the graph T. So this is very strange because this says that the smallest eigenvalue of a graph is very strongly depending on the local structure of the graph. Yes, because we have these two graphs are very local, yes. You only look at two graphs that are neighborhood of a graph, yes. So it is this is strange. This is a little bit strange. So the question is, what is lambda T and what is T exactly? T, we can calculate T of T lambda, but how to calculate lambda minus lambda T? Because that takes a little bit more work to do that. So now we start again with a graph with small eigenvalue, fixed small eigenvalue. And then we take a clique with at least 2 lambda cube vertices. And then what you do is, if you look at a vertex outside C, then either because of this K2 tilde, K2T tilde result, that small eigenvalue goes to -infinity, we can show that either X is associated to almost all vertices of C or almost none vertices of C. So the almost none is lambda squared. And then you can make a relation between the cliques. You make a relation on the cliques, and it turns out that this relation is equivalent relation. That's not so clear, but it can be shown. It's just, you need to show, you need that the cliques are large enough. Now you take an equivalent class of cliques and look at the induced subgraphs induced on the union of free C1, where C1 runs over all the cliques in your equivalent class. Then it can be shown that this is a very dense graph. That means that the complement has larger valency at mod lambda squared. So this is quite a very dense graph. So, And we call Q a quasi-clique, which is close to clique, but it is not exactly a clique. But it is close to a clique, and therefore it's called a quasi-clique. And those quasi-cliques gives quite it gives you tools to study the structure for it. So now we have to introduce a notion that comes from number theory. So some referees don't like that I call it as integral, but it comes from, they like that it will be, they probably prefer as integral, but I will show you why we cannot do this. Okay, so we say an G with adjacent matrix A and small cipher lambda min is as integrable if we look at the following matrix, S times A minus lambda min and then the floor of lambda min times the identity matrix. That is, of course, a positive semi-derivative matrix, so we can write it as N transpose N, but we now want N has only integral entries. And the S integrable terms come from integral lattices in number theory. So we cannot call it S integral, although that is what referees want us to do it, but I think that's not possible. And note that B has only integral entries. So what is a generalized line graph? Is one integrable graph with small cipher at least -2. So it's not so difficult to understand why it is called a generalized line graph, because it somehow has to do with a line graph. And using the quasi-cliques above, Hoffman showed that the connected graph with large minimal valency and small cipher at least -2 is a generalized line graph. So that is what he showed. And a year before, in 1976, somehow Cameron, Goodhouse, Sider, and Shu showed something better, because they showed that if it has a connected graph with small eigenvalue at least -2 and with at least 37 vertices is a generalized line graph. They also show if it is not a generalized line graph, then you can say quite a bit about the graph. We know in principle all those graphs. We know all the maximal graphs, so we know in principle all the graphs that are not generalized line graphs with small cipher at least -2. But the proofs are very different. So that is where the difference is. And Hoffman showed that if you have a large K valency, if your valency is very large, and if your small cipher is less than -2, then it cannot be much more than -1 minus square root of 2. And that is because if you take the part of length 2 times the Cartesian product with a complete graph, that has small cipher -1 minus lambda 2. That's why this, you cannot do better than this. That is what I mean to say. So Cameron, Goodhouse, Sider, and Shu use the classification of root lattices or weak lattices as done by Ernst Wied in the early 1940s. Hoffman did not use it, but his problem is that he has to assume that the valency is, the minimal valency is very large. And with the two Youngs, we generalize Hoffman result to -3. So what we showed is that a connect graph with small cipher at least -3 and last minimum valency is T integrable for T at least 2. We can say a little bit more precise result, but this is, I think, good enough for this talk. But we don't know how to realize the result by Cameron, root outside and shoot for -3. But before you can go there, you first need to but you need to do this before you can realize Hofmann's result to -4. Because you can construct from any -3 graph with small size -4 by taking Cartesian products with a clique, for example. So you have to understand first -3 very well before you can go to even to -4, even for the Hofmann's result. And for the Koolen-Young result, we use the idea of quasi-cliques. This is an important tool there. For our -3 result, we use the result of the KYY paper and show that if G is a sesqui regular graph with small cipher at least -3 and C is at least 9, then it must be one integrable. And then we classify the one integrable ones, and then we got everything we wanted. And this is not so difficult. So now we are going to look at construction. So we look at the S-clique extension. I'm sorry, I cannot use a blackboard here. So what you do, you replace every vertex by a clique of order S. And if the two vertices X and Y were adjacent, then every vertex of CX with CY is adjacent to each other. And if X is not adjacent to Y, then no vertex of CX is adjacent to CY. And if you have sesqui regular with parameter C with small cipher lambda min, then the S-clique extension of G is sesqui regular with this S times C and has smaller eigenvalue S lambda min plus S minus 1. It's all not so difficult to see. So you can construct. So if you start with -3 or -2, then if you take the two clique extensions, you get the graph with small cipher -3. So if you take from sesqui regular with small with parameter C and -2, then you get the one with 2 times C and -3. That's what it's like. So now we look at the K-regular graph with 3 vertices smaller eigenvalue minus lambda. And let be a co-clique of, if you don't like co-cliques, just an independent set of order C. And the Hofmann's bound gives that C is at most this number, phi over 1 plus K over M. This has to do with the Dassault bound. The Dassault bound is for cliques and the Hofmann bound is for co-cliques. And for stronger hierarchy graph, if you take the co-clique of the complement, it's the Hofmann bound on the complement is exactly the same as the Dassault bound on the original graph. And a co-clique is called an Hofmann co-clique if equality holds in this bound. And then you can show that that co-clique has every vertex outside the co-clique has the same number of neighbors in the co-clique that we say E. And the following is inspired by Hamers and Tonshev. So the Hofmann coloring of K-regular graph is a coloring of G such that each color class is a Hofmann co-clique. And this is an optimal coloring. You cannot do better. You cannot color with less color. And the only way with this kind of, with the number of colors in this, then it has to come from this kind of coloring. So now we assume it's co-edge regular with parameter C and having an Hoffman coloring chi. So now what we do is we construct a new graph H from C by adding edges x, y if x is not equal to y and they have the same color. Then you can easily see it's co-edge regular with parameter C plus 2e, where the e is from the Hoffman co-clique. And if you start with a strong array graph, then H has exactly 4 distinct eigenvalues. Hammers and Tonshev show slightly more, but the consequence of their result is that the H has exactly 4 distinct eigenvalues. And this was now I will try to convince you that there are many sesqui regular graphs. Although for -2 you say there are not so many. So if you take the line graph of a regular graph with field at least 5, that is sesqui regular C1. Yes. And for C at least 2, it can be shown that the graph has diameter 2 and hence co-edge regular. And they are classified. So co-edge regular graph with small diameter -2 arc. And they have always C at most 8. This is not exactly true because you will say, yeah, you have also the Peking graph, but except for the Peking graph, all the other graphs have C even. And the Schlafly graph has 27 vertices. And if the number of vertices is at least 28, then C is at most 4. That is also known. And for C is 4, we have the triangular lines, the Sonsky graph J and 2, or if you like it, the line graph of the complete graph for n at least 4. And for S C is 2, we get the S times T grid, and they are also infinite family. And for C3, we don't have any examples. Now let's just look at examples of sesqui regular graphs with small z-value at least -3. We have strong regular graphs. There are 2 strong regular graphs. The Steiner graphs, they're coming from Steiner triple systems, the block graphs of Steiner triple systems that are called Steiner graphs. I will not go into details. And the second family is you can make from a letter square. If you take a letter square, then if you take the coordinates of the letter square, so that n squared coordinates, if you have a letter square of order n, and two of those pairs of coordinates are shaded when they lie in the same row, in the same column, or the entry of the letter square is the same for those 2 numbers, for those 2 coordinates. And that gives you a strong regular graph with C is 8, 6. And the McLaughlin graph is strong regular graph with C is 81. I already mentioned this. I always get confused. Is it the McLaughlin graph or the complement of McLaughlin graph? Because in some sense, it makes no difference which graph you take as a McLaughlin graph. Because the reason why it's called McLaughlin graph, because the McLaughlin group acts rank 3 on this graph. So that is why it's called a McLaughlin graph. So to my opinion, they should be both called McLaughlin graphs, but okay. And an example of sesqui regular graph with C is 10 and diameter 3 is the Gorges graph, and for the Sonsky graph J and 3 we get diameter 3 graphs with lambda is -3 and diameter 3 and C is 4. So we can also take the 2-click extension of the examples with small cycle at least -2. We get 3 families. For C is we get the 2-click extension of the line graphs of the regular graph with at least 5. For C is 4, we get the 2-click extension of the S times T grid. And for C is 8, we get the 2-click extension of the triangular graphs TM. And then we thought that that is all. We don't expect it many more families. For CS4, we get the Johnson graphs of diameter 3. And maybe that will be the end of all the examples, of at least if the number of 30 is large enough. That was what we were thinking at this moment. But then early November, Mr. Ger found that we have more examples. So, and of course, for CS1, it's not easy, not difficult to find an infinite family with unbound diameter. You do essentially the same thing as for the line graph. It is not so difficult to see what you really need to do. Okay. But for CS8, there exists another infinite family. And I somehow already mentioned it. So you take the triangular graph Tn or the line graph of the complete graph on n vertices. Then G has a Hofmann co-clique if and only if n is even. But you can say more for n is even. For n is even, it always has a Hofmann coloring. It's like if you, that's something what we know as a competition. Yes, there's a Hofmann coloring in the triangular graph. So if you add the edges in the Hofmann coloring, one gets a co-edge graph with CS8 at small size -3. Are there more infinite families with CS8? We don't know. I don't think so, but we cannot prove it yet. So. And here I missed, if C is a sesqui graph with parameter C and C is less than K -3 and small cycle, I assume that small cycle is at least -3, is then C most 81. I think this is true, but how do you prove this? I have no idea how you can prove this. And Yingington and others give the following conjecture. So we thought that either if you have only 4 distinct eigenvalues, then either it has is close to the K is close to V, or the S-click extension of a strong Rayleigh graph, or S times T grid, where S is smaller than T. But this conjecture is wrong. So this conjecture is false as the triangular graph with an added Hofmann coloring show. You can probably adding the Hofmann coloring with more than one Hofmann coloring. We are thinking how to do this on this moment. We still have to show that they have on the most 4 distinct eigenvalues, that they are co-edge regular is not so difficult, but whether they, what are the smallest eigenvalue, and that is what we are still studying on this moment. Then if you assume that of the 4 eigenvalues, 1 is -1, then I think the conjecture is still true. But we don't not have a proof on this moment. And if you do not assume is that one of them is -1, then on this moment, I have no idea how to reformulate the conjecture. What is the right statement of the conjecture? And that is all I have to tell you today. Thank you for your attention.
Thank you very much for your talk. Any questions to Jack? Oh, I have one question. Would you please show slide number 26?
Yes.
Yeah, this one. So you were talking about infinite families. So we see equal to 8, right? Yeah. And you said that you don't think that there are some other families, right? Yeah. But what about some sporadic graphs? What do you think?
Oh, they are many. I don't think that there's any way you can classify.
Oh, I see.
There's no hope. Whether we can show that C has to be, or diameter has to be 2, that's not a question. That is, we don't know. Sesqui regular graph with C is 8, that's more side -3, and many vertices, well, that is diameter 2. That's all things we also don't know.
Okay, you said that you know many examples. Well, but what is the way to get them? How did you get them? Some computational results or theoretical results?
I mean, if you start with an association scheme, 3-class association scheme,
Yeah,
then you can get many examples because you take the complements.
right.
And there are many of those examples. I mean,
I see. Yeah, I see. Okay, I see. Thank you very much. Any other questions? Okay, if not, then let us thank again Jack. Thank you very much. It was very interesting, and it is a new topic. In some way, we can share with us this open problem. So it is interesting. Thank you very much. Yeah.
Okay, thank you.
Thank you.